Okay, so today we shall be studying a bit about dual nature of radiation and matter, and we shall be able to solve questions based on dual nature of radiation and matter. So, what kind of questions do they appear in the entrance exam
In
pertaining to
the
these?
entrance exams as well as in the board exams, most of the questions from this chapter
Uh huh.
are all formula based, and you
Okay.
need to remember the formulas
Mm.
and you need to remember constants.
Mm-hmm.
Constants like speed of light, charge on an electron, mass of an electron, and
So on
as
and so
such,
forth.
yeah.
Right.
So
So yeah, can you just give us a brief as to what concepts are related to this particular
okay, let
chapter?
me break this chapter into different parts.
Mm-hmm.
Okay, the first part will consider the dual nature of radiation.
Right.
So in this part, we'll see a few formulae
Mm-hmm.
which are used for solving different problems.
Right.
Number one is E.
Mm-hmm.
E equals h nu
Right.
or hc by lambda.
Mm-hmm.
E is the energy of a photon.
Mm-hmm.
Nu is the frequency. Lambda is the wavelength.
Right.
And as you know, h and c are constants. C is the speed of light in vacuum. It is equal to 3 into 10 to the power 8 meters per second.
Mm-hmm.
And h is Planck's constant, and it is 6.626 into 10 raised to the power minus 34 joules second,
Mm-hmm.
or 4.136 into 10 raised to the power minus 15 electron volts second.
Mm-hmm.
So unless the values are given otherwise, you are supposed to take these values or like approximations of these values to get your answer.
Right.
So here we have a shortcut formula as well,
Okay.
which is hc equals to 12375 electron volt Armstrong.
Right.
So we are going to simplify this further. E is the energy,
Mhm.
and it is 12375 divided by lambda.
So basically, these can be used while solving problems, right?
Yeah,
In the
I have
sense.
included a problem
Mm-hmm.
based on this formula.
Mhm.
So you need to remember such formula, because in the examination, if you are not acquainted with such formula,
You'll have to sit and multiply.
yeah,
That will
you'll
be a
have
lot
to
of time.
sit and do a lot of calculations, and you'll waste a lot of time, and you
Mhm.
might even end up doing mistakes.
Right.
But in this thing, you must remember one fact, that lambda must be in Armstrongs, and energy will be given in electron volt, not in
Mhm.
joules, in electron volt.
Right. 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 Fine. So these are the constants which you need to remember, right? And what else?
Like, let me tell you a basic fact that
Mhm.
when light is propagating, like it is traveling in any medium, then it is the nature of light is governed by its wave properties.
Mhm.
So it will act as a wave, but when it interacts with particles and exchanges energy between light and matter, it is governed by particle properties.
Right. So this is why we call it dual nature, isn't
Yeah,
it?
dual nature, because light behaves as a wave when propagating, and when it is interacting with matter and
behaves as a
particles,
particle.
it behaves as a particle.
Mm-hmm.
So this is the dual nature of radiation.
Mm-hmm.
So we move on to the next part.
Okay.
which
So the
is-
particle nature of light.
Yeah, the particle nature of light.
Mm-hmm.
So for the second part, we have a momentum of quantum of light.
Mm-hmm.
Quantum of light, as we all know, is basically known as photons, because photons are packets having energy, and they are the constituents of light.
Right.
So momentum of a quantum of light is given by h nu by c. H is the Planck's constant, which I gave the value earlier.
Mm-hmm.
Nu is the frequency, and c is the speed of light, which was also given earlier.
Right.
So next is the intensity I. The intensity is given by delta E divided by S delta T.
Mm-hmm.
S is the area, surface area, where the light is incident. Delta T is the time interval,
Mm-hmm.
and E is the energy that is transported in this while radiation is falling on a surface.
Right.
So intensity is basically the energy transported per unit area per unit time.
Okay.
So next we move on to the radiation pressure.
Mm-hmm. So radiation pressure, what I understand by radiation pressure is the pressure which is experienced by the surface due to the radiation emitted on it.
Yeah, that is correct. When if there is a surface and some light or any radiation, electromagnetic waves, etc., fall on this surface, and when it is either absorbed or reflected back,
Mm-hmm.
there will be a certain pressure exerted on this surface that is known as the radiation pressure.
Okay.
So as I told, it can be either absorbed or it can be reflected. So both of them have different radiation pressures.
Right.
So if it is totally absorbed, you have this formula, that is the intensity divided by the speed of light c.
Okay.
And if it is totally reflected, you have it as intensity divided by speed of light c multiplied by 2. That is, it is twice the pressure caused when it is totally absorbed.
Fine.
So we'll be using this formula in different, like in a problem later. So you need to remember all these formulae, because in this course as well as in different competitive exams, anywhere, you'd be able to solve the problems only when you know the formula.
Fair enough. Okay, so what about the next one would be emission of electrons?
Yeah, the third part is emission of electrons. And here I'm not giving any formula, I'm just telling a few basic definitions and things that you need to know.
Definitely.
Yeah. So first is the work function. This is a very important concept, the work function. That is the minimum energy required to emit electrons. If there is a surface and light falls on it, when will this light be able to emit the electrons? Certainly the electrons are bound to the surface. Otherwise, if there would have been no force pulling the electrons, then if there is a random surface, electrons would start coming out of it.
Yeah.
Don't you think that is like, otherwise if that was the case, we would require no energy to generate electricity.
True.
But that is not the case. So there is something that is holding the electrons to the surface.
Yes.
So to overcome this something, we need a minimum energy that is known as the work function of the metal.
Okay. True. So work function is basically the minimum energy required to emit the electrons.
Yeah.
Right.
Work function is going to be used in a lot of problems of photoelectric effect.
Okay.
It's like a fundamental stone where you can't ignore this, because this is going to come in almost all the problems that we are going to do.
Right.
There are different types of electron emissions. So we are going to discuss about thermionic emission. Thermionic emission is when, if you heat a surface, heat a metal or something.
Yeah, the heat energy will provide the energy to emit the electrons.
Yeah, heat energy would be used to overcome the work function.
Nice.
So again, we go to the work function, because that is going to come in all the electron emission concepts.
Right.
Any energy you give has to be more than the work function.
Okay.
And the electrons that are emitted due to this heat supplied are known as thermions. Next we have field emissions. Field emissions are the electrons which are emitted due to applied electric field. The electric field is externally applied to emit the electrons from a metal surface.
Okay.
So the electrons are emitted in opposite direction of the applied electric field. Do you know why?
What does that mean? No.
This is because the electrons are negatively charged.
Oh, okay.
So when the electrons are negatively charged, the field in which direction is applied, the electrons are bound to move in the opposite direction.
Right. Brilliant. Okay. So this is field emission, is it?
Yeah, that is field emission. Then we have secondary emission. It is like some electrons or high-speed particles, different atomic level particles, if they strike a surface, and if they collide with an electron, this electron might get enough kinetic energy to move out of the surface, because it has more energy than the work function.
Right.
So this is caused by bombardment of high speed electrons or other particles. Other particles include other atomic particles.
Right.
So this is called secondary emission. And finally we have the one which we'll be discussing most in this chapter.
The most famous one.
Yeah, the photoelectric emission. So this we are going to discuss in detail later. It's caused due to incident light on a surface, and it emits electrons known as photoelectrons.
Right. So let's move on to the next page. So the fourth part.
The fourth part, the photoelectric effect. As I was saying earlier, I'm going to discuss photoelectric effect in detail here.
Right. So photoelectric effect has been talked about a lot. So yeah, can you just give me a brief as to how it happens generally?
Yeah, so here, if this is a metal surface, and if electrons are here on the surface, And if light of certain frequency falls on the surface, this photon would give the energy to this electron, and if this energy is more than the work function, this electron will move out.
Right.
This is called a photoelectron,
Okay.
and the
This
phenomena
the
is known as
yes.
photoelectric effect.
Fine. So these are the formulae related to it.
Yeah. So firstly, we have E is greater than equal to W naught. E is the energy given by the photon, and W naught is,
the
as
work
we
function.
all know, it's the work function. So energy must be greater than or equal to the work function.
Or else
Otherwise,
there is no photoelectric effect.
photoelectric effect is going to take place. As we all know, E can also be written as h nu, where nu is the frequency, h is the Planck's constant. This was given in section 1. I told about this in section 1 when we were talking about dual nature of radiation.
Right.
Yeah. So this has to be greater than the work function,
Okay.
or the frequency has to be greater than work function divided by the Planck's constant. We can say this because Planck's constant is a constant, and we take this to the other side, and this we get this condition. So
Okay.
we have a minimum frequency like below which there will be no photoelectric emission. This is known as the cutoff frequency or threshold frequency, known as nu naught, which is equal to W naught by H.
Okay.
Similarly, we can take the same analogy to wavelength as well, because
because we know frequency is C by wavelength.
C by lambda. Yeah. So the same way we have this conditions, hc by lambda greater than W naught, or lambda must be less than W naught by H, and the maximum wavelength lambda naught is known as the threshold wavelength. Like if the wavelength is more than that, then there would be no photoelectric emission, and that lambda naught is equal to Sc by W naught.
Right.
So these are the variations of the same formula, but you need to remember each of them properly, because you never know when a problem would come and which formula you need to apply.
And which parameters are given in the question.
Everything would depend on what data is given in the question and which formula you need to apply. Okay, so next we move on to a very important thing. Note that wave theory would suggest that kinetic energy depends on intensity. This intensity is important.
Okay.
But maximum kinetic energy is EV naught, which is independent of the intensity of the light.
Right.
So this was a fundamental theory of wave theory, which was challenged by this photoelectric effect. So then people moved on to this wave particle duality. Before that, light was considered to be a wave.
Right.
So this is something that we need to remember, because we might get questions where they vary the intensity, but kinetic energy would not depend on the intensity. It will depend on EV naught, or it will depend on the frequency of the incident radiation.
Okay.
So we have maximum kinetic energy equals to E minus W naught. E, as we all know, is the energy of the photon.
W naught is a work function.
W naught is work function,
which is also equal to H nu minus
nu naught.
So H nu is E and H nu naught is work function.
Yeah.
Perfect.
Nu naught is the threshold frequency, and as we all know, nu naught equals to W naught by H. So H nu naught is the work function.
So this is Einstein's photoelectric effect.
This is the most important equation that you need to know for photoelectric effect. It's Einstein's photoelectric equation. So next we have the maximum kinetic energy is mv square by 2. That is basically coming from classical mechanics.
Right.
That is half mv square, if you would like to say it that way. And then it is also equal to ev naught. So E is the charge on an electron, and V naught is the stopping potential. So V naught is a potential. If you apply this against the photoelectrons coming out of the surface, then there will be no photoelectric emission. That is the minimum voltage required so that photoelectric emission stops. That is known as stopping potential. Yeah. So next we move on to the fifth part.